For those of you joining us on the recording, thank you for tuning in. We wanted to start with going over the kind of content of the exam as well as the exam kind of format. So, for the exam, it is 5 multi-part questions. And by multi-part, I mean part A, part B, part C, part D. These questions are all short answer, which means no multiple choice. So keep that in mind, right, when you are starting these. Additionally, this exam is worth 45 points. And there are 4 extra credit points up for grabs. Now you may be asking, all right, Mr. Bruce, right? But like what's actually on this exam? And, you know, that's a fair question. So the topics for the exam include, we have dimensional analysis, so dimensional analysis is 1, classifying, and balancing, chemical equations, you have nomenclature, and full/net ionic equations. The extra credit is extra credit that is around this unit. So it's not anything from semester 1, nor is it anything from that we're going to be doing next unit. All the extra credit is just harder problems from this unit. For the extra credit, you've got a choice of 2 problems. I won't spoil what the problems are, but they do fall in one of the topics that are here. For the exam as well, you will get 60 minutes. So those are kind of the parameters of the quiz of the exam. So that way you kind of know what you're expecting as you are going into it. Again, whenever you have a question or whenever you would like, really feel free to go ahead and type a question into the chat. I go over questions in the order that they are received, unless there's a question that I spot that kind of ties in with the content that we're going to be going over. Sure. There's a question here about balancing chemical equations, and specifically balancing chemical equations where we may need to double things, right, in order for us to get a good kind of grasp on it. Let's do this. Let's say let's do a good first easy one to start, and then we'll go into a more complex one. Let's say we've got nitrogen gas reacts with hydrogen gas to yield ammonia gas. As a reminder, right, all these G's mean these are these states, which when you're balancing things really doesn't kind of matter. When I was first starting off, I always like to make a chart, right? Kind of look at what is going to be happening. So in my chart, some of you may be able to do this in your head, and if you can, that's great, but we'll start off here. I count up what's on the left and what's on the right. So for my nitrogens, I say, okay, looks like I have 2 nitrogens. So I'm going to go ahead and put a 2 here. On the right, I've got 1 nitrogen. So I'll put a 1 there. Okay, how about hydrogens? Okay, looks like I've got 2 on the left, but 3 on the right. In order for this to be considered balance, both sides be equal in order for something to be balanced. So here, if I look, not both sides are balanced. It's not a great thing. So I need to go ahead and decide, what could I multiply something over here by in order to get 2 ends? What if I put a 2 here? Now, important thing, right? You can only put the 2's, anything in the coefficients of the equation. You can't change any compounds. This 2 you multiply into it. So instead of 1 compound, now I've got 1 nitrogen, now I have 2. Instead of 3 hydrogens, I have 6. Now I ask myself, is both sides equal? Let's check. Nitrogens are equal, that's good. But my hydrogens aren't. So the only other place where I could do hydrogen things is over here. I need 6 on this side, so 2 times 3 is 6. And bingo was his name mode. And that is just the big thing. You box that up, call it a day. Now, what happens if we have stuff that we can't super easily balance, right? Where do we kind of start with those? And that's a great question. I will go ahead and write one down for you. Just give me a second. Let's try this one. Let's say I have C3H8 plus O2 yields CO2 plus H2O. So here, the first thing, of course, we do is make our chart. Okay, we make a nice little handy dandy chart. Right, okay, looks like we've got carbon, hydrogen, and oxygen. 3 and 1, 8 and 2, 2 and 3. Left, right. So, all right, looks like I need to put a 3 here because I need 3 carbons on this side. Now you may be asking, whoa, why aren't we just starting with the oxygen? The reason is because both of these compounds have oxygen in them. So we don't really want to be messing with just oxygen if we don't have to, right? Here we can also adjust the oxygen pretty easily just on this side, right? Just here. It's harder to adjust over here and get it perfect. So we're going to kind of ignore that for now. We'll do that later. All right, looks like that means I've got an updated count of 3 and 6 plus 1, 7. All right, let's look at my hydrogens. Okay, looks like I need a 4 here, right? 2 times 4 is 8. And that also updates my oxygen count. So I've got 8 here, and 4 plus 6 is 10. Okay, look here. Need a 5 there. 10. Call it a day. If you are ever stuck in balancing in an equation, try doubling your most complex thing. Now, what do I mean by that? If you're ever stuck, sometimes it helps to double the most complex thing, which in this case would be this. Looks like our next part here is about kind of explaining what do we mean by nomenclature, right? What are we expecting with that? And that's a fair question, right? We didn't do a ton with nomenclature. We kind of hit on it at the beginning of the semester, but what are we expecting? Great question. Pretty much for nomenclature, we will give you a small list of chemicals, and it kind of goes into net ionic and full ionic reactions when you need to kind of decide what is going to react with each other. So let's say, for example, we have calcium chloride. And we have sodium hydroxide. And our task here is to kind of figure out, 1, if they react, and 2, what the equation would be. So this is where it kind of comes into play of our nomenclature. Watch. So with calcium hydroxide, calcium has a 2 plus calcium chloride, apologies. Calcium has a 2 plus charge. Chlorine has a 1 minus charge. So when you do your crisscross, you get CaCl2. Right? We got to add that together with, I will also call this aqueous, with aqueous sodium Na with a 1 plus, and then hydroxide 1 minus. I get this hydroxide here from the back side of my periodic table. So yes, we are still using polyatomics. We're going to be using them for the rest of the year. We're going to be using nomenclature for the rest of the year. So you should always expect, if we give you names of chemicals, we're expecting that you know those chemical formulas. You may need to do your crisscross every time, but soon you won't have to. CaOH, and that's also aqueous. Now you may be asking, okay, like how do I determine kind of what this turns into? And I say that's a great question, right? Because our next question here is going to be, do calcium chloride and do sodium hydroxide react with each other? And if they do react with each other, what do they make? So that's the question we're asking ourselves here. And you might be saying, Mr. Boots, I don't know how to do this. That's okay. We're going to kind of show you. We're going to take our first thing, our cation from our first reaction, from our first compound, and mix it with the anion of the second compound. Okay. Don't forget that the plus goes before the minus. So here I have calcium, Ca, with a 2 plus charge, reacting with OH, which has a 1 minus charge. I do my crisscross, and I get Ca parentheses OH2. We're going to skip the states for right now. We'll get to the states here in a moment. Okay, let's add this together with, all right, what are the two things we haven't reacted with yet? There it is. We've got the sodium here reacting with the chlorine. Or in other words, the sodium Na with a 1 plus charge, and the Cl 1 minus NaCl. All right, now comes the fun part. We need to determine, does this reaction occur? We determine this by using the solubility rules. Each of you at some point were given a small half sheet with solubility rules, right? There was green and red and kind of showed a bunch of little things. You're going to be getting the same sheet on the upcoming exam. And it's all this is determining how you use it. That's it. I look on the little sheet. It says, okay, all chlorides are soluble except with, and it says 3 things. We check, is sodium one of those 3 things? Check. No, it isn't. So that means this is aqueous. That's good, right? That's fine. I look here. Okay, calcium and hydroxide. It says here hydroxides are insoluble in water except with group 1A metals and ammonium. Calcium is not a group 1A metal, nor is it ammonium, which makes this, you guessed it, would be our solid, would be our precipitate. The next question here with this is, sorry, there's one more kind of small question here is how do we write charges? Your charges always get written with the number before the state of the charge. So that's 2 plus 1 minus. It's just kind of how chemists do it. So before we move into the dimensional analysis, which is our next question, I'm going to go ahead and actually kind of skip to the question that we're kind of currently on, which is, all right, what's our next step here? What do we do now with this entire thing? All right, what's next? Great question. Right, this is the molecular equation, right? The ME. Your next step here would be writing out the full ionic equation. It's your next step. All the full ionic is every single compound except your solids get broken up into aqueous compounds. All get broken up into the ions. For example, this CaCl2 gets broken up into a calcium ion with a 2 plus charge and a calcium ion with a 2 plus charge that's aqueous, and 2 chlorine ions with a 1 minus charge that's also aqueous. The question here might be asked, okay, where does that big 2 come from, right? Where is it coming from? Good question. This 2 here comes from there. So we're just taking that count and putting it right there. That's aqueous. Now this, we also got to split up our sodium hydroxide. So we got to add this together with sodium, Na with a 1 plus charge. That's also aqueous. And our hydroxide, OH, with a 1 minus charge, that is aqueous. Now, I actually forgot a step here. If you take a look at my molecular equation, what did I not do? If you're yelling at your screen right now saying you didn't balance it, you're absolutely correct. So you quickly balance it, choom, choom, and you put those numbers in front of them as well. Right, so that big 2 here, right here, came from there. Same thing with this big 2, it came from there. All right, you may be asking, okay, well now what, right? Okay, it's a great, thing. Again, we got to split up our aqueous compounds. So we've got 2 Na with a 1 plus charge, that's aqueous, and 2 Cl with a 1 minus charge, that's aqueous. And now, question here is, do we separate our solid? No, your solid stays together. CaOH2. Solid. And that would be your full ionic equation. Okay. Quick coffee break, really quick. Nothing better than coffee. Now you may be saying to yourself, Mr. Booz, this is too long. It's like 8:30 p.m. I don't really want to write all this. Guess what? Me neither. And guess what chemists did back in the day? They didn't want to either. So instead, they came up with the net ionic equation. The net ionic equation, all I care about is what things made our solid. Green. So here I'm looking at what stuff made my solid, which is here. Okay, I look here. Okay, looks like my calcium made my solid, and my 2 hydroxide ions also made my solid. So guess what I'm going to put for my net ionic? Just those 3 things. That's it. Calcium, which has a 2 plus charge, that's aqueous, plus 2 hydroxide ions, which are also aqueous, and this yields our solid CaOH2. And bingo, was his name-o. Right? That's it. There ain't no funny business here, right? Chemists back in the day were as lazy as you, right? They wanted to make things efficient. That's why they developed the net ionic equation. So let's start from the top. You may be asked first to make a word equation, right? The word equation, all it is saying calcium chloride reacts with aqueous sodium hydroxide to yield aqueous sodium chloride and solid and solid calcium hydroxide. Then you go into your balanced molecular equation, then your full ionic equation, then your net ionic equation. The order doesn't matter for the net ionic equation. As long as your because these 2 things here, right, they could be flipped and it'd still be technically correct. The question here, there's another question here. When did this kind of 2 move? And that's a great question. This 2 moved here when we did our crisscross here. So we get this 2 came over here. This 1 came over there. So the question also here is, why can't the 2 go onto the Cl? And that's a good question. It's because Cl2 does not equal Cl1 minus, right? This here is a compound. This here is an ion. Good question. Solid usually comes last. It's just kind of a format sort of deal. Correct. For when solving problems that involve writing the net ionic and ionic equations, it will always be aqueous and solid forms for the products and reactants. Correct. Will there ever be any results that are ever liquid or gas? If so, how do we tell what they are? For the exam, there will not be. The best ways, kind of how to identify them, is if we get H2O in the products. But for this exam, there won't be any that do that. Are there more solubility rules other than the ones that we need to know on the sheet? No, and besides, you're going to be getting this sheet anyway. You should balance in this situation. I just definitely didn't forget to do that at all. So on the test, will the question be posed as, what is the nomenclature of Ca whatever? No. The nomenclature on the exam is like, consider you've got 4 compounds. Like, let's say you've got, calcium chloride, sodium hydroxide, lead 2 sulfate, and, mercury 4 nitride, right? Which ones will create a precipitate? So it's all about you knowing kind of, okay, how can I format this? So going back to the top now, right? Kind of, there was a long little tangent into the world of net ionic and kind of ionic equations, where you only do net ionic and full ionic for your double replacement reactions that create a precipitate. That's the last important bit there as well. There was a question here really quickly that I want to cover about talking about how do you classify these chemical reactions, and then we'll get into dimensional analysis, because I did see a couple questions at the top. They just didn't really fit right then and there, so we'll do those after classifying chemical reactions. For those of you who remember, there were 5 different types of chemical reactions. You had synthesis. Synthesis reactions had A plus B yields AB. So when 2 or 3 things come together to make one thing. You had decomposition, which was AB breaks down into A plus B, or 2 things broke up, or 1 thing breaks up into 2 things, or 3 things breaks up into 3 things, or 1 thing breaks up into 3 things. You've got single replacement, which you've got something that is kicking out something else. Right, so there in that example, the A is kicking out the B. Double replacement, which is your AB plus CD yields AD plus CB. And of course, your last one, which is your combustion. And combustion is always something. This something is usually a hydrocarbon. A hydrocarbon is a compound that has hydrogen and carbon, obviously, and sometimes oxygen in it. Think methane, CH4, octane, C8H18. This reacts with oxygen gas to yield always H2O and CO2. All right. I promise we go over dimensional analysis next. Let's do that now. A lot of you are stressing out about dimensional analysis, and I understand it's a pretty scary thing, right? It's just, but in all honesty, you all have been doing it every day in your entire life. We're just kind of showcasing it in a different way. For example, right? If you ask yourselves, okay, how many days are, if there are 5 months or 5 weeks until spring break, how many days is that? 5 times 35, or sorry, 7 times 5 is 35. Okay, let's say that there are 4 years until, the next leap year or something. How many more weeks do you need to wait? Okay, 4 times 52 is, that's it, right? You've been doing this all your life. This is just a separate way of thinking about it. For example, let's say I have 7.75 inches. And I want to convert this into centimeters. Okay. If I want to convert this into centimeters, we need to do a little bit of dimensional analysis. Observe. Now, your next question here is going to be, are we going to get conversion factors on the exam? For example, right, how 1 inch is equal to 2.54 centimeters? And the answer is yes, you will get those. The only ones we will not give you are like time related. How many months are in a year? How many weeks are in a month? We're not going to give you those. So here I've got 7.75 inches. And I know that in every 1 inch, I get 2.54 centimeters. Key thing here, key. This unit, oh, I don't like that color. This unit here needs to be the same as this unit. You may be asking, oh, why, Mr. Boos? The reason is because they cancel each other out. Because guess what? At the end of the day, I don't want centimeters. I don't want inches. I want centimeters. So now what I do here is I have 7.75 times 2.54 centimeters over 1. So I pull out my handy dandy little calculator. And I do 7.75 times 2.54. And I get this is equal to 19.685 centimeters. Pause. You may say, great, right? Fun. Your answer would be marked as incorrect. The reason is because whenever we are dealing with measurements, we always have to use sig figs. Now you may be saying, well, how do I know how many sig figs to round to here? Good question. You determine how many sig figs you need to round to by looking here at your initial measurement obtained. Here, I have 3 sig figs. So that means your final answer needs to have 3 sig figs. And again, we know it's 3 sig figs because that's what we started off with. We'll do another example, but don't forget to round to sig figs if you have measurements. Right? If you have measurements, that's the most important thing to do, is round off at the end. Let's do another one. We'll do another dimensional analysis, and I'll go back to the questions that I see about net ionic and kind of no reactions. What do we do there? Good questions. Let's say, okay, la di da di da. I have let's say I've got 18.07 ounces of coffee. And I want to figure out how many grams of coffee do I have? It's a great question. Your conversion factors for this are, for every 1 pound, oh, sorry, I don't want to find grams. I want to find pounds. Apologies. Oh, no, I want to find grams. For every 1 pound, it is 453.6 grams. And for every 1 pound, it is equal to 16 ounces. So I'm going to go ahead and give you all half a minute to start solving this on your own. I'm going to refresh coffee, and we'll come back here in just a moment. All right, let's do this thing. So I'm starting off with 18.07 ounces. Now here, I can't go directly from ounces to grams. I got to make a pit stop. I got to make a pit stop in pounds, which is awful, but we have to do it. So I do a multiplication here. I know that in every 16 ounces, that's 1 pound. And I know that from this relation there. Additionally, I know that in every 1 pound, I have 430 or 453, apologies, 0.6 grams. Now you may be asking, whoa, there's 3 fractions here? Yes. Because observe, this ounces cancels out with this ounces. This pounds cancels out with this pounds. So what are you left with? You're left with grams. So if all these cancel, waching, I'm left with 18.07, right? 07 times 1 times 400, oh boy, times 453.6 grams over 16. And guess what? I put it into my calculator exactly like this. I put 18.07 times 453.6 divided by 16. And I get 512.2845 grams. Question: am I done? If you said no there, you would be correct because I've got to now round it to sig figs. Second question: how many sig figs should I round this to? If you said 4, you're correct. But why is it 4? And it's because I look here. I always look at the starting measurement, not any of the other junk that's in there, because those are facts. We look at the starting measurement. Starting measurement here is 18.07, which is 4 sig figs. So that means my final answer needs to have 4 sig figs. And bingo, what's his name-o? Lethal dosage dimensional analysis questions will not be on the exam. So, the other question here is, do we need to show all of our work for dimensional analysis? Can I just put that in the calculator and call it a day? You got to show all your work. And I apologize, but you got to show it all your work. Predicting combustion reactions is not going to be on the exam. So I hope that we're kind of moving and grooving here. There's a couple kind of oddball questions I'm going to kind of hit now before we dive into going back into a little bit more of the net ionics and full ionics. There's a question here: what is a compound compared to an ion? A compound is something like this, where you've got no charges, no nothing, right? No charges, no nothing, right? No charges, no nothing, right? An ion is just a singular thing with a charge. That's it. We did a nomenclature example. We did how do we deal with sig figs. We did some nomenclature examples. You will have multi-step dimensional analysis problems. You will be given the conversion rates for everything. There will be no lethal dosage, no lethal dosage, no lethal dosage. I can scroll back down to the answers for dimensional analysis. There we go. The level of difficulty for these dimensional analyses are going to be a little bit more tricky. They're going to be mostly two-steppers, so kind of keep that in mind. There will be maybe one step, but mostly two steps. So expect two steps. We'll go back to the nomenclature kind of stuff here in a moment. Uh, some of the balancing equations will be simpler. Some of them will involve doubling your stuff. So you got to be kind of on top of it. Let's do one more. We'll do two more kind of net ionic and full ionic things. To kind of showcase that. You should expect kind of the level 3, maybe level 4, right? If there was a little, even one more above that in FET, which there isn't, but they are going to be tricky ones, right? We need to make sure that you kind of know what you're going to be doing. That's why I recommend the table. The table is very helpful. We'll need to find combustion. Let's do one of these that doesn't form a compound or that doesn't have a reaction. So let's say we are going to be reacting magnesium chloride and ammonium nitrate. And we need to figure out, does a reaction even occur here? So let's do it. So this is where your nomenclature kind of stuff comes into play. Magnesium chloride. Okay, magnesium, Mg has a 2 plus charge. Chlorine has a 1 minus. MgCl2 aqueous. Okay, I'm combining this with ammonium nitrate, which is NH4 with a 1 plus, NO3, 1 minus, NH4, NO3. And this would be aqueous. All right, now I got to do our kind of foil-esque type of deal. So my magnesium goes here, and my chlorine goes here, and I get Mg NO3 to aqueous. I know it's aqueous because all nitrates are aqueous, right? That's from that little half sheet. And plus, we have ammonium NH4. And then what is this? Cl. We'll need a 2 here and a 2 here. Now, the big thing here is our second one going to be aqueous or solid? If you take a look at that little half sheet, you will see that it is aqueous. So because they are both aqueous, there will be no reaction. So then what would be our full ionic? Our full ionic would be Na, because it's showing kind of what makes her solid. I know for the lab sometimes you had to write it out, but that's just because we wanted you to get practice with it. Now that we're applying it, you don't need to. And with the net ionic, this would also be Na, because there is no reaction. We'll leave that there for right now while I drink some coffee. FET is a kind. We did that in class. I know MRS, I think, did it for the cold day assignment. My class, we did it in class. It's kind of just like an online simulator. Yes, you would put it in front. Let's do one where you will need to do it in front. We'll kind of check those off as we go. That's correct. Not anymore. You don't need to. So, because guess what? On the exam, it's going to ask you verbatim using one that creates a precipitate. What will be the net and full ionic equations? So, let's cover that one. We'll use red. Let's say I have strontium nitrate and sodium sulfide. All right, let's go through this one. Strontium nitrate, that formula is aqueous plus, we'll actually make it smaller. We're going to run out of room otherwise. What do we got? Sodium sulfide, oh boy, Na2S aqueous. This yields, okay, strontium and sulfate or sulfide goes together. SRS, and then we'll determine if that's solid or aqueous here in a moment, plus NaNO3. Now, again, if we look at the little half sheet, we know that all nitrates are soluble. So, this would be aqueous. And SRS, if we look at the little half sheet, it'll say, oh, now, all sulfides are insoluble unless they're with a group 1A metal. Strontium is not a 1A metal, ergo solid. Okay. Now we got to do our balancing. Looks like our balancing is actually going to be pretty easy here. Looks like we just need a 2 here. Oh, bam. Call it a day. This is the molecular equation. Now, again, as a reminder, for your full ionic, these are all aqueous compounds broken up. Right? All of them, no matter what. The only one you don't break up is the solid. The solid stays together. Our first aqueous compound is here right at the front. We've got SR. SR has a 2+ charge, and that is aqueous. And we have, the question here is, how many nitrates do I have? Here we have 2 nitrates. Two nitrates, and I get that from here. 2 NO3, 1 minus. Whoa. Why did I not take away that 3 that's on that nitrate? The answer is because that 3 is stuck to that nitrate. We can't move it. If you look on the back side of the periodic table, the 3 comes with it. Can't remove it. That's also aqueous. plus, okay, looks like I've got two sodiums, Na at a 1 plus charge, that's aqueous, plus a sulfur that has a 2 minus charge, that is aqueous. And this yields, we're actually going to zoom it down. Okay, looks like we have two sodiums, Na with a 1 plus charge, and that is aqueous, plus two nitrates, NO3, the 1 minus charge, that is aqueous, and solid strontium sulfide. That would be our full ionic equation because everything is split up. All my aqueous compounds are split up, regardless if they help me make the solid or not. So now we need to just identify what things make our solid. Then we're donezo. Okay, SRS is our compound that we need to make. So that means we need a strontium with a 2 plus, that is aqueous, plus sulfide, which has a 2 minus, that is aqueous. And this yields SRS, solid. And that would be your final answer. Now, on the exam, we're only going to ask you to do one of these, with the idea that you're going to have a kind of like in the practicum where you had 4 different combinations. You're going to choose one that works, and then do it. Sure, we'll return to the nomenclature problem in just a minute. For the net ionic and full ionic, will we get points taken off if we put charges where they don't belong, like in the net ionic? Yes. So that, like, if you put charges like here, you would get points off, or if you put charges up here, you would also get points taken off. Right? You only put your charges on your aqueous ions. That's all of these little guys, or these ones too. Nothing else. Now we hit the answer for dimensional analysis. We did a nomenclature. We did that. We did that. We can do a difficult one. Sure. Give me just a moment. So the question here is, can we do a difficult equation to balance? Now that everybody's kind of done looking at this one, we're going to scooch just back up to our nomenclature stuff. Right, the nomenclature stuff is just here. It's all about writing out your compounds. That's it. You would get points off if you don't put charges in full and net ionic. Will we have the conversion factors for the dimensional analysis conversions? Yes, you will. We'll do this one in the. We'll do the hard to balance one, and then we will cover it we'll call it for the day. Will we need to know simpler conversion factors like millimeters to meters, etc.? The answer is, of course, yes. All right. Let's say I've got a behemoth ready. Let's say we have this equation. C3H8O plus O2 yields CO2 plus H2O. That's a good one. This is where it separates the okay. I don't know. Anyway, I've got my handy dandy little chart here. The stuff on the left, stuff on the right. We've got the carbon, hydrogen, and oxygen. Okay, carbon's on the left, 3. On the right, 1. Hydrogen's on the left, 8. Hydrogen's on the right, 2. Oxygen's on the left, 3. 1 plus 3. Sorry, 1 plus 2. And the ones on the right, we've also got 3. All right, question. Is this balanced? Shouldn't take you too long to decide. If you said no, you'd be correct. It ain't balanced, right? Whatever's going on here doesn't work. Okay. So I'm going to say, looks like my copper, or not my copper, my carbon atoms are all out of whack. So let's fix those. I've got 3 on the left, but I need 3 on the right. So I'm going to go ahead and put a 3 here. All right, we're just going to put a 3 there, kind of see if that works. All right, updates my carbon. Oh, and it also updates my oxygen count too. 3 plus 1 is 7. Okay. All right, everything good? Everything balanced? No, it ain't. Now I got to do my hydrogens. And again, why aren't I touching my oxygens right now? It's because we can pretty much easily adjust my oxygens on the other side really easily without it kind of fixing it all right now. So let's focus on our hydrogens next. Our hydrogens, I've got 8 on one side, 4 on the or 2 on the other. So if I put a 4 here, this would get us 8. Oh, and we got to update our oxygen counts too. Looks like we've got 10. All right. Now we're going to be in a little bit of a pickle. We got 7 oxygens initially on the right. So the question is, I'm going to undo what I just did for a student question. You were asking, how did I get 7 here? If you look carefully, I've got 6 here. 6 plus 1, 7. That's how I get it. So if I put a 4 here, now I've got 6. Right, 6 here plus 4, 10. Great question. Do we need to know how to balance the other types of equations? Yes. Now, is there any way I can adjust this 2 alone to get 10? I could put an 8, right? That's pretty easy, right? Or sorry, I could put like a 4 here, but then I get 9, not 8. I'm kind of stuck and I don't know what to do here. If you're ever stuck, the best thing to do is double your most largest chemical. The most scariest one, double it. So because I'm stuck, I'm going to, I got to pull the trigger. Got to double it. Kind of ruins all our entire good work, but let's see if it'll make everything easier on the other end. Okay, this updates a lot of all of my counts on this side. I've got 6, 16, and 4 oxygens, 2 plus 2. Okay, now let's get rid of these because they're no longer kind of useful. So I've got 1, 2, and 3. Again, 2 plus 1 is 3. All right, I've got 6 oxygens on the right side. Okay. Or sorry, I've got 6 carbons on the left side. I need 6 on the right. So I need to put a 6 there. Big ol' 6. Okay, that updates this and that updates this. That's 6. 6 times 2 is 12 plus 1 is 13. Okay, let's look at my hydrogens. I've got 16 on the left side and I've only got 2 on the right side. Does combustion always result in CO2 gas and H2O gas? Yes. Uh, 16, so that means I'll need an 8 here. Oh boy, that changes a lot of stuff here, right? We got to change this and change the big one. So now I've got 16, and now I've got 12 plus 8, which is 20. Now here's the real question. The real question to ask yourself right now is what goes here? This is where it gets a little tricky because you may just say, oh, I know that. It's 10, right? 10 times 2. If you put a 10 there, you get 22 oxygen atoms on the right side. Because we already have 2 here. So we need to incorporate that. So if I've already got 2 here, what number do I need here in order to make it work? And if you said 9, you would be correct. And that would be your final answer. You will not have to create an equation of synthesis, decomposition, single replacement, or combustion. You will just have to create ones of double replacement. The question here is, why is it 9 and not 5? Great question. If we put a 5 here, we're going to be stuck with 12 oxygens on this side because 5 times 2 is 10 plus 2 is 12. And I've got 20 over on this side. So that wouldn't work, is really the biggest reason why. Where can I go to find difficult practice problems like this? Personally, for this one, I just put it in ChatGPT and said, create a problem that you have to double the biggest thing. Some other good examples, right? There are a lot of worksheets online that have this sort of problems. I believe PhET has some really good ones. The textbook as well has some amazing problems as well. ALEKS has some good problems. The problems you want to do in ALEKS are the chemical reactions with conflicting integers or something along those lines. How would you balance other equations like your synthesis and decomposition? You balance them the same way you balance anything else. You use your chart. The simpler conversion factors you should know for dimensional analysis are like your May King Henry died by drinking chocolate milk, Mike. There was one last question for tonight. We've called last question. There will be no more questions after this one, partly because we are about 15 minutes over. And I want to respect my time. If you've got something like this, NO, I don't know, 3, and it breaks down into N2 plus O2, right? This would be a decomposition, right? Because it's splitting up one thing, it's splitting up into 2 things. That was just a specific question I asked at 9:04. All right. I think that does it. So if you have any further questions that were unanswered tonight, or if you want additional practice problems, please feel free to reach out. My email is sboos@depaulprep.org. I'll be up probably for the next 2 hours, and I'm happy to send out extra problems. I hope that this meeting was helpful to everyone. We're going to go ahead and stop the recording. If you tuned into the recording, thanks again for tuning in. And I'll see you all in class.